The browning of white adipose tissue, where energy-storing white fat takes on the thermogenic and metabolically active characteristics of brown fat, is a powerful adaptive mechanism that enhances energy expenditure and combats age-related obesity. This transformation depends heavily on mitochondrial biogenesis, lipid turnover, and cellular remodeling processes that require efficient autophagy. As organisms age, the capacity for white adipose tissue, WAT, to undergo this browning transformation diminishes, largely due to declining mitochondrial quality and suppressed autophagic activity. Nicotinamide mononucleotide, NMN, through its ability to raise NAD+ levels and activate nutrient-sensing pathways such as SIRT1 and AMPK, has emerged as a potential agent to reawaken this browning process by restoring autophagic flux and supporting mitochondrial remodeling within adipocytes. At the cellular level, browning involves a shift in gene expression and morphology. White adipocytes typically store energy in large, unilocular lipid droplets and contain relatively few mitochondria. In contrast, beige-brown adipocytes of smaller, multilocular lipid droplets are rich in mitochondria and express uncoupling protein 1, UCP1, which allows them to dissipate energy as heat. This transition is energetically demanding and requires the removal of dysfunctional mitochondria, the breakdown of excess lipid, and the biogenesis of new, more active mitochondria, tasks in which autophagy, and specifically mitophagy, plays a pivotal role. Without efficient autophagic recycling, this transformation cannot proceed at scale or sustain thermogenic function. NMN supplementation acts upstream of this process by restoring NAD+ levels, which are required for sirtuin activity, particularly SIRT1 and SIRT3. SIRT1 activation leads to deacetylation of transcriptional coactivators like PGC-1A, a master regulator of mitochondrial biogenesis and oxidative metabolism. PGC-1A promotes the expression of UCP1 and other genes involved in thermogenesis, while also enhancing autophagy-related pathways. SIRT3, located within mitochondria, further ensures the quality and efficiency of newly formed mitochondria by activating antioxidant enzymes and stabilizing the electron transport chain. Both of these processes are fueled by NAD+, and thus supported by NMN administration. In parallel, NMN-induced activation of AMPK, a central energy sensor, further promotes autophagy by inhibiting mTOR and activating ULK1, the kinase that initiates autophagosome formation. Through these mechanisms, NMN creates an intracellular environment favorable for both the clearance of dysfunctional organelles and the generation of new, high-functioning mitochondria. In experimental models, NMN supplementation has been shown to increase markers of autophagy, e.g., LC3-2, ATG5, in white adipose tissue, alongside enhanced mitochondrial density and UCP1 expression, hallmarks of browning. These effects are significantly attenuated when autophagy is genetically or pharmacologically inhibited, supporting the idea that NMN's browning effects are autophagy-dependent. This connection between autophagy and mitochondrial remodeling is especially important in aged adipose tissue, where the accumulation of damaged mitochondria and lipid droplets impairs the cell's ability to transition into a thermogenic state. By promoting mitophagy, NMN helps clear these metabolic bottlenecks, allowing adipocytes to respond more effectively to browning stimuli such as cold exposure, adrenergic signaling, or exercise. Moreover, by reducing inflammation and oxidative stress, conditions that suppress browning, NMN indirectly supports a tissue microenvironment conducive to thermogenic remodeling. Importantly, NMN's ability to enhance browning is not merely a cosmetic shift in adipocyte identity. Beige adipocytes improve systemic insulin sensitivity, increase whole-body energy expenditure, and may even secrete beneficial adipokines that regulate liver and muscle metabolism. In this sense, NMN's role in inducing browning through autophagy can be viewed not only as a local improvement in fat quality, but as a systemic metabolic upgrade that counteracts the energy imbalance and inflammatory burden associated with aging and obesity. Human data on NMN's effects on adipose tissue browning are still limited, but early trials show improvements in markers of mitochondrial function and insulin sensitivity, which are indirectly tied to adipocyte thermogenic potential. As research advances, The combination of NMN supplementation with external browning stimuli, such as cold exposure or exercise, may offer a promising strategy to maximize these effects in older adults or those with obesity-related metabolic impairments. In summary, NMN appears to promote the browning of white adipose tissue by restoring autophagy, particularly mitophagy, and supporting the mitochondrial remodeling necessary for thermogenic function. This autophagy-dependent mechanism enables a functional shift in adipocyte metabolism from energy storage to energy expenditure that offers tangible benefits for metabolic health and weight regulation. As part of a broader effort to reverse age-related metabolic rigidity, NMN's capacity to reprogram fat cells into metabolically beneficial beige adipocytes represents a powerful therapeutic avenue grounded in the biology of cellular renewal and energy adaptation.